So section 3.1 is exponential functions and their graphs. Now you guys have probably heard people refer to something that is increasing or growing at a fast rate or is growing really quickly, exhibiting exponential growth. And that's just not always the case. Let's think about this scenario. So my nephew Jonas, he saved up his money from doing all his chores, and there's now $100, and he's decided to deposit that $100 into a savings account instead of just storing it in his dresser drawer. This is a very smart decision on Jonas's part, but why? What's the difference between storing his money in his dresser drawer versus a savings account at a bank? So let's think first about if he were to put that $100 in the dresser drawer. A year later, there would still be $100, assuming he didn't add anything or take anything away. It would be a nice surprise, right, if he opens up his dresser drawer and there's $100 sitting there, but there would still be $100. 2 years later, if he puts it back in the drawer, 2 years later, there would still be $100 in the drawer, right? His work or his money just would end up sitting there unless he were to do additional work and add to it. Versus if he puts that money into a savings account at the bank will actually end up paying him interest. So let's say that every year, and this would be a high percentage, but just to make it simple, let's say that this savings account pays 5% interest annually. And the bank wants your money in the savings account. The banks want the money in the bank. And that's kind of the incentive for putting your money in the bank, is that they will pay the interest. So then they can use that money for loans, which they can charge even more interest. And that's how they can kind of make their money. So whenever he puts his money into the bank at year 0, so let's call that t = 0. He has $100 that he's put in there, and I missed my 1. Okay, so a year later, if the bank pays 5% interest, he would then have $105 in the bank. He didn't even have to do any extra chores or anything. The money's just sitting there, and it's gaining interest. Okay, so his money is making money just by sitting in the bank. And then let's say after 2 years, if he didn't add anything else, if we took 5% of 105 and then added that to the 105, we would have $110.25. And after 3 years, if we took 5% of 110.25 and added that to 110.25, we would have, or Jonas would have, $115.76. So his money is just making money. And if we're taking 5% each year, and that amount is getting larger and larger and larger, the amount that we're adding on is also going to end up getting larger and larger and larger, so that his money will be increasing at a faster rate as time is passing. At first it's kind of slow, but then once his money starts getting to larger and larger amounts, it's going to end up making more and more money. So that's why it's a smart decision for Jonas to put his money in the savings account instead of putting it in his dresser drawer. And his money is actually exhibiting exponential growth. Our intuitive definition for exponential growth or decay, that was an example of growth. Decay is if the initial amount is decreasing, is if you have a quantity or an initial amount, which in the above example, the initial amount would be $100. So if you have a quantity or an initial amount that increases or decreases exponentially, will grow or decay by a common percentage per period. So each period in the above example is a year. So the period is equal to 1 year. And that common percentage is 5%. So this money is increasing 5% each year. And you can probably think of some other examples. We'll discuss together some other examples of quantities that grow or decay exponentially. I'll just put a couple on here. So in biology, you guys will talk about population growth or decay. So that population, you can end up talking about population growth or decay. And population in biology, you guys will talk about how the Earth's population at one point for a period of time was exhibiting exponential growth. But then there are kind of these external constraints or based on limiting resources that have actually switched population to be more of a logistic growth, where the growth kind of has leveled out. And again, you guys will talk about that more in your biology classes. As another example, an example of exponential decay could be like with medication. So like if you let's say you take Tylenol for a headache, you take a dosage, the amount of Tylenol in your body, in your system, is going to actually decay exponentially. Like you've maybe in other classes, like in your chemistry class or one of your science classes, talked about like the half-life of something. So how long it takes for half the amount to be there, or it to decrease the amount to decrease by 50%. So medication, we can talk about exponential decay. Cells can multiply or grow and exhibit exponential growth. For a while, COVID-19 was exhibiting exponential growth. Back in March and April of 2020, we were often in the news. They were giving information about the doubling time, so how long it would take for the number of cases to double or increase by 100%. Okay, so here's our formal definition of exponential growth or decay. So an exponential function is in the form y equals to a times b to the x power, where a can't be equal to 0, b must be strictly greater than 1 or between 0 and 1. B is called the base, where b is a real number with the restrictions stated above. A is the vertical stretch or shrink factor, and also the initial value, as well as the y-intercept to the graph. So let's think about what would happen if b was equal to 1. So if we looked at any of these constraints that are stated above, or the restrictions that are stated above on what a and b are, let's see what would happen if any of those were true. So what would happen if b was equal to 1? Well, if the base is equal to 1, you would have y equals 1 to the x power. Well, if you raise 1 to any real number, so if you were to plug any real number in for x, 1 raised to that power would just be equal to 1. So that y equals to 1 is just a horizontal line. if b were negative. So let's come up with an example. Like, let's say the base was -2. Let's make a table here to see what would happen. So I'm going to use 1, 2, 3, 4 for values for x. So if I plug 1 in for x, y would be equal to -2. If I plug 2 in, -2 squared would be 4. If I plug 3 in, -2 raised to the third power, that's -2 times -2 times -2 would be -8. And if I plug 4 in, that would give me 16. So you can see that the values for y are oscillating or bouncing back and forth between positive and negative values. So when something is oscillating, it's bouncing back and forth. Oscillate. Oops. And if a were equal to 0, well, that would just simplify to be 0. So we would have a horizontal line at y equals to 0. Okay, so let's look at, now our focus in this chapter is not going to be on graphing, but I want you to understand that you can graph exponential functions using the same types of translation or thinking about graphing from a translations transformations perspective. Before we do that, let's go ahead and look at the graph of a couple exponential functions. So very simple exponential functions. Let's change colors too. So if we graph y equals 2 to the x by plugging in these values for x, we're just making a table of values. I would have y equals 2 to the -2nd power. Remember, exponent rules, that would be 1 over 2 to the 2nd power, so 1/4. And if we plug in -1, that's going to be 1/2. And when we plug in 0, that simplifies to 1. And 2 to the 1st is 2. And 2 squared is 4. So I can plot those points. So -2, 1/4. -1, 1/2. 0, 1, 1, 2, 2, 4. And if I were to continue on, like if I plug in 3, 2 cubed is 8. So that would be a sketch with some points of the graph of y equals to 2 to the x power. And then y equals 2 to the -x. I'll use green. So notice if I plug in -2, that's going to end up being 2. Or sorry, 4. That would be 2 squared, which would be 4. If I plug -1 in, though, then y equals to 2. And then that's still 2 to the 0th, which will be 1. And 2 to the -1st is 1/2, thinking exponent rules. and 2 to the negative second power is 1/4. Again, thinking exponent rules. So plotting those points, -2, 4, -1, 2, 0, 1, 1, 1/2, 2, 1/4. And if I were to plug in -3, we'd have -3, 8. That one does not want to make the nice curve. So that's y equals 2 to the negative x power. And again, remember, I just said that we could think about graphing exponential functions using the same translations transformations. That negative is happening to the x, or x is being multiplied by -1. That indicates, if we thought of y equals to 2x as the parent function, that indicates a horizontal reflection, or a reflection about the y-axis, which that's what these graphs look like, right? And then let's just look at these graphs a little bit closer. Switch back to purple for y equals 2 to the x. The domain, so what values can we plug in for x and still have a real output? Well, the answer is any real number. So the domain would be negative infinity to positive infinity. The range, well, let's think about this. Why don't we actually determine end behavior before we determine the range? So let's think about as x approaches negative infinity, what does y approach? And as x approaches positive infinity, what does y approach? So as x approaches negative infinity, let's think about plugging smaller and smaller values. Now, if we plug, we already plugged -1, -2 in, and we saw we got 1/2, 1/4. If we plug like -100 in, -1000, so 2 to the -1000th power would be 1/2 to the 1000th power. Thinking about using exponent rules to rewrite that. If we plug in -1 million, -1 billion, -1 trillion, right? We would keep rewriting that as 1/2 raised to a really large number. So the denominator would keep getting larger and larger and larger while the numerator can't keep up, meaning that our y coordinates of the points are going to end up approaching 0, but they'll never be equal to 0. Like there's no real number that you could plug in for x that would end up giving you 0. And then as x approaches positive infinity, you can see the graph looks like it's trending towards positive infinity, but then also if we just think about plugging in larger and larger values, 2 to the 1000th power, 2 to the 10,000th power, 2 to the 1 millionth power, right? Those values are just going to getting really like larger and larger and larger, meaning that the function will approach positive infinity. So because as x is approaching negative infinity, y is approaching 0, that actually indicates that the equation that could describe the end behavior of this function would be a horizontal asymptote at y equals to 0, right? Think about when we were analyzing end behavior for rational functions, the same thing happened. Anytime the function was approaching a number, there ended up being a horizontal asymptote that we used to describe its end behavior. This also helps us with determining the range I already said there's no real number that we could plug into the function that would make y equal to 0. So we would say that the range, reading the graph from bottom to top, would be from 0, where 0 is not included, to positive infinity. And then for y equals to 2 to the negative x, domain is also all real numbers. And then the range, for those same reasons, although it's flipped for which, as x approaches which infinity, the range will end up being also from 0 to positive infinity. But for end behavior, we would say as x approaches negative infinity, y is approaching positive infinity. And as x approaches positive infinity, y approaches 0. So again, that indicates a horizontal asymptote, right? This statement here indicates that a horizontal asymptote can be used to describe the end behavior of this function. So the parent function, if we want to graph these functions using translations and transformations, we're always going to be thinking of the parent function as being y equals b to the x. So for these two functions here, the parent function would be y equals 3 to the x. So if we graph y equals 3 to the x, let's just think about plotting a few points. So if we were to plug in -1, we would have 1/3 as our y coordinate. If we plug in 0, we'd have 0, 1. If we plug in 1, 1, 3. If we plug in 2, 2, 9. Okay, so connecting those points. Okay, and if you did the same analysis as we did for y equals to 2 to the x or y equals 2 to the negative x, you would see that there is a horizontal asymptote. I should have sketched it in the above graphs, but there's a horizontal asymptote at y equals to 0 on the parent function. So to graph A, f of x equals to 3 to the x plus 2, that plus 2 is a horizontal shift. It's happening to the x. So it's a horizontal shift left 2. So each point on this graph of the parent function will be shifted to the left 2 units. So nothing has happened to the shape. Okay, and then we'll use pink for g of x. Okay, so g of x equals 3 to the x plus 2. So that's that plus 2 is a vertical shift up 2. So each point on the parent function is going to be shifted up 2 units. I'm off the graph slightly. Now when we do the vertical shift, the horizontal asymptote also has to shift up 2 units. So the horizontal asymptote would actually be at y equals to 2. oh, that's not y. I should use their proper names. So pink was g of x, blue was f of x. Okay, and let's do one more. Again, the point here is that you can graph these functions using the same translations and transformations that you guys are familiar with. So I would actually rewrite h of x as negative 2 to the negative x plus 1, because remember we do the shifts last. So we take care of any reflections, stretch, shrink, before we do horizontal and vertical shift. All right, the parent function we have already graphed above, and that's y equals 2 to the x. So we are familiar with some of the points, right? Negative 1, 1/2, 0, 1, and 1, 2. So let's think about translating those and transforming those points. And reading the equation for h of x from left to right, when I'm listing the translations and transformations, there's first a vertical reflection, then a horizontal reflection, and then that plus 1 is a vertical shift up 1. So taking the point that was at negative 1, 1/2 and applying the vertical reflection, we would be at negative 1, negative 1/2. And then the horizontal reflection would put us over at 1, comma, negative 1/2. And then a vertical shift up 1 puts us at 1, 1/2. The point that was at 0, 1, vertical reflection would be at 0, negative 1. Horizontal reflection wouldn't go anywhere. Vertical shift, we're up at the origin. The point that was at 1, 2, vertical reflection is at 1, negative 2. Horizontal reflection, we're at negative 1, negative 2. Vertical shift up 1, we would be at negative 1, negative 1. And if you wanted to use another point like 2, 4, vertical reflection, we would be at 2, negative 4. Horizontal reflection would be at negative 2, negative 4. Vertical shift up 1, we're at negative 2, negative 3, just so we could have another point. Now, the horizontal asymptote, which would have been at y equals to 0. Vertical reflection doesn't go anywhere. Horizontal reflection doesn't go anywhere. But that vertical shift shifts it up to y equals to 1. Okay, so that is the graph of h of x. Okay, so next let's talk about the natural base e. And you'll see 2 and 10 as common bases for exponential functions in applications, but you'll also see the irrational number e, which is called Euler's number, named after Leonard Euler. And e is referred to as the natural base. So the number e comes from evaluating the expression 1 plus 1 over n raised to the nth power as n approaches infinity. So that expression, as you keep plugging larger and larger values in, ends up approaching the value of e, which it will be important for you guys going forward to at least remember an approximation of e. And the approximation of e that you should have memorized is 2.718. It's kind of like how maybe back in junior high or earlier you memorized pi as being approximately 3.14. You guys should know the approximation of e is approximately 2.718, although E has its own button on the calculator, which I'll show you guys, and we're going to want to use that. But just to help us with graphing points, E is approximately 2.718. Okay, and then if we are graphing y equals e to the x, let's graph that first, and then e to the negative x will just be a horizontal reflection. So let's make a table of values to graph y equals e to the x. Okay, so if we plug in -1 for x, that's approximately 0.37, because that would be 1 over e. So approximately 0.37, I'm going to attempt to graph that. If we plug in 0, we get 0, 1. Notice anytime we're plugging 0 into a parent function, we're getting 1 as the output. Okay, when we plug in 1, we get the approximation of e. And if we plug in 2, that's approximately 7.389. So again, if we want to graph e to the negative x, that's just a horizontal reflection. So I'm reflecting each of these points, across the y-axis. And there is no vertical shift, so both of these graphs, again, think end behavior, will have a horizontal asymptote at y equals to 0. Okay, so here are some other examples of exponential functions. Let's determine if each of these functions is exponential or not exponential. So we'll put a capital E if it is exponential, a capital N if it is not exponential. So f of x equals 7 to the x power is exponential. F of x equals x to the 7th. That looks familiar. Not exponential though. X to the 7th, remember, is a polynomial function. We just studied those. X to the x, f of x equals x to the x power. Well, there is a variable in the exponent position, but the base can't be a variable. So not an exponential function. This is actually referred to as an aleph. And I'm maybe not pronouncing this correctly. But an aleph function. D would be exponential. F of x equals 4 times pi to the x power would actually be exponential, right? Pi is a real number that would fall into the restrictions of our definition of an exponential function. F, not an exponential function because you can't have 1 as a base. This would actually just simplify to be equal to 3, which would actually be a horizontal line. G is exponential. F is not exponential. Remember, the base cannot be negative. This graph would actually oscillate between positive and negative values. Base can't be 0, right? This would end up simplifying to be equal to 0, but only for whenever x is strictly greater than 0, right? If x were negative, or even if x were 0, that would be undefined. So not. And then this is a tricky one. F of x equals to 3 over 4 to the negative x. Using exponent rules, this could be rewritten as 3 times 4 to the positive x power, because we could get rid of that negative exponent by bringing it to the numerator. So this is an exponential function. And our final examples. Find the exponential function f of x equals b to the x, whose graph is given. Okay, well, let's see. We can see the point 0, 1, and then the point 2, 25. Okay, so what exponential function, when raised to the second power, what base, when raised to the second power, would give us 25? That you could even set up the equation, because we know another point on here. 25 equals b to the second power, where b would end up having to be equal to positive 5. Remember, can't be negative, so can't be negative 5. So the function that describes this graph would be y equals 5 to the x power. And then looking at this other graph, we're thinking, okay, well, what base, when raised to the third power, would have an output of 1/3? Or what number, when raised to the third power, would give us 1/3? So I could set up the equation 1/3 equals b cubed, right? What base, when cubed, would give us 1/8. 1/8 equals b cubed. So b, if we took the cube root of each side here, we would get 1/2. So the equation that would describe this graph would be 1/2 to the x power. And you do need that parentheses. This could also be written as 1 over, so if you're thinking exponent rules, this could be written as 1 to the x, which you know would just always be equal to 1, and then 1 over 2 to the x power, because you apply that exponent to the numerator and denominator. This could also be written as 2 to the negative x. And we are going to stop here. So before we look at some of the formulas for exponential growth and decay that Cynthia Young gives us in our textbook, I have another lesson where we come up